All right, class, today we're studying section 4.8, rational functions with vertical and horizontal asymptotes. We're going to be able to determine domain and range, find intercepts, asymptotes, and holes, describe end behavior, and sketch complete graphs. A rational function is one that is a quotient of two polynomial functions. In general, it means that I have an x in the denominator of my fraction. The domain of a rational function is that which the numbers do not cause a zero in the denominators of fractions. So, if I look back at these previous examples, I take this middle one. The domain is every number except for the number that causes the denominator to equal 0. So if I take my denominator and set it equal to 0, the graph would be undefined, or the function would be undefined at x equals negative a half. I would express that in my domain like this. I would say negative infinity to 1/2, and then negative 1/2 to infinity, effectively leaving out all the number negative a half. The properties for intercepts are the same as any function. The y-intercept occurs at the point where x equals 0, provided that the graph is not undefined at that point. So all I have to do is plug in 0 for x. X-intercepts occur where the numerator equals 0, provided the graph is defined at that point. So if we take a simple rational function, 3x plus 1 over x, to find the x-intercept, I set it equal to 0. So the first thing I would do would be to multiply by x to get rid of the fraction. So essentially, I really only care about where the numerator equals 0, provided that whatever number makes the numerator 0 also does not make the denominator 0 as well. An asymptote is an imaginary line that the graph cannot cross in its extreme points. A graph can contain horizontal, vertical, and oblique asymptotes. If you look at this first sketch, there are asymptotes at x equals 0 and around x equals 2. It gives our graph this kind of half and half shape. Now in the second picture, it appears that we have an asymptote at x equals 0 and a vertical asymptote around x equals negative 3 and a vertical asymptote around x equals negative 2 or positive 2.5. Now this asymptote where y equals 0 for the horizontal, notice the graph does cross the horizontal asymptote in the middle, but it's the extreme points that we want to focus on for our horizontal asymptotes. Vertical asymptotes occur everywhere where the denominator equals 0, but the numerator does not. So our focus is looking at where the denominator equals 0. A horizontal asymptote has several rules that we need to pay attention to. You always want to first make sure that you are comparing a reduced fraction. So make sure that you cancel out any common factors. If the degree of the numerator and the degree of the denominator are the same, then the horizontal asymptote occurs at the fraction of the coefficients. So for example, 3x plus 1 over 2x. The degree of the numerator and denominator is the same, so there would be a horizontal asymptote at or on the line y equals 3/2. Just make a fraction of the leading coefficients. If the power of the numerator is smaller than the power of the denominator, then the horizontal asymptote occurs at the line y equals 0, like in this previous example here. And if the numerator is larger than the denominator, we won't have a horizontal asymptote. We'll have a slant asymptote, and we will talk about that at a later date. The easiest way to determine end behavior is to simply plug in numbers that are close to the asymptote. Find the vertical asymptotes, horizontal asymptotes, holes, if any, and sketch the graph. So let's first off determine our vertical asymptotes. Our vertical asymptotes occur where the denominator equals 0, where the function is undefined. So I will set the denominator equal to 0, subtract the 5, and then divide by -2. So I have this particular function where it is undefined at x equals 2.5. So let me get my graph paper out. And I'm going to go ahead and draw my vertical asymptote at x equals 2.5. 1, 2.5, about right there. I typically draw my asymptotes as dotted lines because the asymptotes don't exist in the function. They just cause and give the function its shape. So let's talk about a horizontal asymptote. I have to look back at my rules. If the degree of the numerator is bigger than if the degree of the numerator and the degree of the denominator are the same, the horizontal asymptote versus a fraction of the coefficients, which I think is my situation here. I have this fraction and this fraction. And I compare their degrees, noticing that they're both the same. So the horizontal asymptote will occur at the line y equals -3x over, or 3 over 2. Or -1.5. I'm going to make a horizontal asymptote at -1.5. So this creates the shape of my graph. It might also be in my best interest to go ahead and find the x and y intercepts. The y-intercept occurs where x equals 0, so I will plug in 0. 3 times 0 minus 6 over 5 minus 2 times 0. So I have -6 over 5. So my y-intercept occurs at 1 1/5, -1 1/5. So it's the point x equals 0, y equals -1 1/5, which is right about there. So that gives me part of my shape. I know that the graph will have to exist here. But before I draw that line, it looks like I have an x-intercept that I could determine. So I'm going to set the function equal to 0 to find my x-intercept. First, I multiply to get rid of the fractions, effectively eliminating the bottom here. Add the 6 and divide by 3, so x equals 2. So there's my x-intercept, at x equals 2. Your graph is going to approach the asymptotes, but never actually touch them. So this is one side of my graph. And now to test the other part, I need to pick a point in the other section. Since this is a function, I know I will not have any portion of the graph be down here. So I'll test a point, an x value, how about 1, 2, 3, 4, x equals 4. That'll tell me where my function is going to lie. So if I plug in 4, 3 times 4 minus 6 is 12. 12 minus 6, which is 6 on the top of the fraction. And 5 minus 2 times 4, so 5 minus 8 is -3, -2. So the point 4, -2 exists on my graph, which is right about there, which means that the second portion of my graph has to exist in this section of the asymptotes. Again, it won't exist here because it wouldn't pass the vertical line test at that point. We'll cover more of this in class, but I did want to show you how these particular functions work. Please write down any questions that you have, and we'll go over them.